In today's video, we will look at centrality measures particularly we will look at closeness and betweenness centrality, right. And then there are a bunch of interesting centrality measures, right. So, the first of them is something known as closeness centrality. Right. So, this essentially tries to compute what is the how far a node is from every other node in the network. So, that would be called farness. You invert it, you get closeness, right. So, you essentially compute for a given vertex, you compute the distance between all other vertices. This is farness. You take a reciprocal of that, that is closeness centrality. There are different such measures. So, dg is basically distance on the graph G. So, we always talk about the graph V comma E, where V is basically the set of vertices, or maybe I should call it dg. Right, this would be a slightly better notation. Right. So far we have only looked at degree and between degree to, okay, what is your question?
The distance between two nodes in what sense, the shortest distance or?
Always shortest. D is
geodesic.
Geodesic. Okay, now that you asked that, let us just take a small detour and we look at some a very interesting concept, right. So, there is a whole branch of graph theory known as spectral graph theory, which studies basically a bunch of matrices. So, you all know one very interesting matrix that is connected to graphs, which is the adjacency matrix. This is basically yes, this is an adjacency matrix, it could be weighted whatever, right. And there is a Laplacian matrix which is basically D minus A, and D is basically a diagonal matrix where dii is degree of the ith node, it is 0 otherwise. There are many interesting properties of these matrix. So, the eigenvalues of this matrix will give you clustering in the graph, a bunch of interesting properties like that. I will let you to study a little more on that, but let us just come back to the adjacency matrix. And can you tell me what is A square? Maybe I should reserve this for the lab and you actually try it and figure out what it looks like.
The length to connections.
Exactly. So, a to the 1 essentially tells you if there is a path of length 1 between a node I and j. A to the 2 basically will tell you if there is a path of length 2 between I and j, and a to the 3 will tell you if there is a path of length 3 between I and j. You have to just do the matrix multiplication and convince yourself of this. This is actually a pretty cool trick to use paths.
A to the 2 is not a square.
A squared, it is a squared.
So how will we get?
Because you will multiply a sigma aij bjk, right, to get to. So what is okay, let us look at what is a squared, right. So it is sigma aij ajk, right. So this basically tells you if there is a way to go from I to j and then j to k, right. So two ways of getting there, right, essentially that. So just look at it closely, you will be able to see that. So the ikth element is going to be given by sigma aij ajk for, in fact, across all j's and k's, right. So I should put a, yeah.
How the k is summed over?
Sorry, not k, it's just j.
So if you are interested in,
So you will have 3 for loops, right, when you do a matrix multiplication. So
if you are interested in like after what stage everything becomes 1 and no zeros are there in a power, and that is the,
that would be like your diameter or something like that, but yeah, it would not be the most efficient way to compute the diameter. But you could do something like you can actually do e to the a even, right, that will tell you if there is a path at all in some sense, right. E to the a is actually, what is e to the a? Yeah, so it is basically, no, it is not a, no, it is I, no, I plus a plus 1 plus x square by factorial 2. Right, this is e to the a, although this is really not how you would compute any of these things. It is just fun to know about it, and in fact as we will see in the MATLAB session, this is how you get it, exp m of a. So far we have only been looking at, in a sense, individual nodes, right. There is nothing that tells you a little more about the network and by virtue of its position, about a node by virtue of its position in the network and so on. So the next concept is quite interesting, it is called betweenness centrality. What does betweenness mean? It tries to measure how often a node is between two other nodes, right. How often is a given node sitting on a path between two other nodes, right. So can you think of how this might be calculated? It is essentially a fraction of shortest paths that pass through a given node. Starting from any node across all possible nodes. So we essentially define CB of V as for all S and T. So sigma S T number of shortest paths between S and T, and sigma st of V is the number of shortest paths between S and T that pass through V. V can't be SS or T. So, you ignore edges, you do not consider edges to be paths, the first step.
V is not summed over, right?
No, it is only, so I should, V also belongs to V, but it is summed only over S and T, all S and T. So, this is between a centrality. Let us just look at a small example. So, here what is the between a centrality of C? So, the the definition I gave, the explanation I gave you is somewhat approximate, right. So, if you look at this, this is what is this? Is this the fraction of paths going through a node? It is sum of fractions of paths, right. So, the first thing you need to do is to enumerate the shortest paths. So, let us just try and enumerate the shortest paths. ABC is the shortest path, ABCD is the shortest path, ABCD is the shortest path, AB is an edge. So, as we said S not equal to T, not equal to V, right. So, you do not consider whenever the, so BCD, BCDE, CDE, is that right? So, you have 5 nodes, right. How many shortest paths will you have? 5 choose 2, because all nodes are kind of in the same connected, they are all connected, right. There is no node that is hanging separately, minus 4 edges, which is 6 shortest paths accounted here. So, we have all the shortest paths ready here, right. So, now let us do. So, first let us look at CB of C. So, what are all the paths that C passes through? I mean pass through C this. So, it is going to be 4 by, yeah, it's at the terminus, no. So, we said S not equals to T not equals V. It is actually 4 by 4 equals 1. So, for all S and T, so between A and D, A and E, B and D, B and E, sorry, it is actually 1 plus 1 plus 1 plus 1, no. Let us make it a little harder or somewhat more interesting. We now have a new node F. Now, what are the shortest paths? ABC is the shortest path, ABCD is no longer a shortest path, it becomes AFD.
Sir, we are doing it for C, right?
Yes.
So, everything divided by everything.
No, right. So, Just hold on. Let's finish this example and get back to it, right. So, you basically compute, so S and T is first A and D, then A and D and so on, right, for all possible S and T's, right, you cycle over all S and T's. You can finally again normalize it, right. So, if you finally want to rank it and so on, we will try to take a look at it when we do the network biology lab maybe tomorrow or so. So, you have A, B, C, A, F, D, right. What happens to this becomes A, F, D, E, right, is that right? Yep. Then you have B, C, D is still the shortest path, B, C, D, E is still the shortest path, C, D, E is still the shortest path, F, D, E is also a shortest path. And then you have F, A, B, F, D, C, F, A, B, C is not a shortest path. So, actually this does not turn out to be a very good example. I think I need to turn this, right. Let us just work with this now. Right. So, now what are the shortest paths? A, B, C is the shortest path, A, B, C, D is the shortest path, as is A, F, E, D. Right. So, you will see that the betweenness of B and C will now drop, right, because only half of the shortest paths between A and D pass through C. A, F, E, D, what else? So, A, B, C, A, B, C, D, A, B, C, D, E is no longer a shortest path, it is just A, F, E, and B, C, D is still a shortest path, B, C, D, E is a shortest path, as is B, A, F, E. B, A, F is the shortest path, C, D, E, F is the shortest path, C, B, A, F is the shortest path. You have to actually worry about it in all the other directions as well, but as long as you do one direction correctly, there is no problem, right. It is an So, how many paths should you have? You should have 6 C2 minus 5, right, which is basically 10. We have listed 1, 2, 3, 4, 5, 6, 7, 3, 7, 11. So, some of them there are alternate paths, so that is okay. So, the
give the number of all paths, no? 62 minus 5.
all pairs of nodes.
Yeah, but paths of all pairs of nodes. It won't give the
Number of shortest paths. It will tell you what are the number of pairs of nodes between which you have to find a path. So, AC is a node, AB is not a node. So, AC, AD is done, AE is done. Now, BA is not to be worried about, BF is done, BD is done, BE is done. So, then CA we do not need to worry about, we will only look at in one direction because ABC is already there. CF, so we have CBAF and CDEF, that is done. Then CDE is missed out. you have CDE, and then you have DEF, then you have, there is still one missing path I guess. But essentially if you now start looking at CB of C, right, so it will be 1 plus half plus half plus half. So in fact this is not 1, right? I think there is one more missed path that we have missed.
So it's 62 and 6, so it should be 9.
Oh yeah, that is right, we added 2 edges, not 1. Fair enough. So now this is going to be .5. So if you see this number by itself is not very helpful, right. You need to look at it in the context of other numbers that you have. See, if you had a number between 0 and 1, it is nice, right. You can say something is 1, you know, all shortest paths pass through it, something is 0, no shortest path passes through it. But now you have different numbers, so you need to normalize them. So we will look at this when we do the lab session, where it will become a little more clearer. Okay. There is a very identical concept called edge betweenness, but I think we will just hold on to it. Or let's just finish up with edge betweenness. So Shreya, is there a mistake?
Why is it 1.5? I got 2. Like BCD, between B and D there is only one shortest path and it's
Oh yeah, this is a mistake. So this is again 1, yeah. That is right. So how would you extend this concept to edges? This essentially computes the betweenness of a given node in a network, right. You can extend the identical concept to edges, which is edge betweenness. How many times does an edge occur between other edges, right? You look at all the same paths, but instead of looking for, we were now looking for C, right? Instead now you start looking for say BC or something. So BC occurs once here, only once in fact, and so on, right? So you basically look at how many times a single edge occurs between other edges in a given network, and you also have a very similar concept called co-betweenness. So co-betweenness is basically very similar to edge betweenness. Here if you say, it means that AB should have an edge between them. Here AB need not have an edge between them, right. How many times are paths passing through A and B in the network? So you take a list of shortest paths like this and you just count how many of them pass through A and C, something like that. So AC does not have an edge as far as this network is concerned, right. So this tells you some sort of relative importance of two nodes. BC, no. So you can choose to define it in whichever way, right. You can either ignore edges or keep edges, but usually we ignore edges, we only look at paths, but it really does not make a difference, right. It will sort of add a little bit of redundant information to every measurement, right. So we usually choose to leave out the edges, fair enough. So in the afternoon we will continue with this, maybe finish through this slide finally. It's almost done, we only have like a small bunch of concepts. I won't bother much about motifs, we will do motifs much more seriously in a later class. So we will just look at connected components and we will be done with that. So I hope you had a good introduction to various centrality measures in today's lecture. I encourage you to go and read a lot more about centrality measures. There are many centrality measures that have been developed to study different kinds of properties in different types of networks. In the next video, we will look at some more network concepts such as connected components, and I will give you a quick introduction to network motives, which we will study in greater detail a little later on.